work with my advisor, Iftach Hayat. So really, the first thing we should be asking ourselves when we talk about coin flipping is, what is coin flipping? So I'll try explaining using an example. Let's say we have three parties, Alice, Bob, and Charlie, that want to go see a movie in the cinema. And there are only two screenings, either Alice in Wonderland or Bob the Builder. Obviously, some of the parties have predispositions towards what movie to see. So to be as fair as possible, they've decided to go see a random movie. And they lead a very busy work life, so they want to communicate and decide what movie to see over an online messaging app, like WhatsApp, for example. So they begin engaging in some sort of protocol. Every party sending messages, perhaps even using some private randomness to generate them. And in the end, they decide on an output bit representing which movie to see. The problem is that some parties, some parties might be colluding and attempt biasing the protocol towards a specific outcome. For example, Alice and Charlie might be colluding to ensure that the movie selected is Alice in Wonderland. And this was first formalized by Blum in '82. Under his formulation, the honest parties output a common, hopefully close to uniform bit, even when an adversary controlling some of the parties attempts biasing them. Attempts biasing that bit. And really, this is a fundamental task in cryptography and also in distributed computation. At its core, coin flipping protocols are used to create a public randomness source from many different private randomness sources. But actually, there's much more into it. So lower bounds on coin flipping protocols induce limitations on the stability of random processes in general. Later on, we're going to see how lower bounds on coin flipping protocols induce poisoning attacks on online learners. And this was first introduced by Mekhujifa and Mahmoudi in '19. And coin flipping has many different models varying in the adversary's power, the communication power, and so the communication model, and so on. But we're going to focus on one specific model, the full information coin flipping model, introduced by Benno and Linial in '85. And in this model, all communication is done solely over a single broadcast channel. For simplicity, we assume that every round of communication consists of exactly one party sending a message. In addition, the output bit must be a deterministic function of the transcript. And last, the adversary is assumed to be computationally unbounded. This model gives us a clean and mathematical formulation to our problem. So now that we know what coin flipping is, we want to understand what good coin flipping protocols are. So to that end, we define resiliency. So we say a protocol is T-resilient if the common output bit cannot be fully biased by an adversary controlling at most T parties. So this means that the protocol is resilient in some sense to T corruptions. So the better the protocol is, the more resilient it is. Excellent. So now let's review some of the history in the field. So on the one hand, we have static adversaries. This is very much understood and a bit out of scope for this talk. We're going to focus mainly on adaptive adversaries. These are adversaries that can decide which parties they wish to corrupt along the protocol's execution. What do I mean by that? Well, I mean that if we go back to our example, the adversary can decide to corrupt Alice, for example, if and only if Charlie sends the message 3. So to be precise, we give the adversary an opportunity to corrupt every party before every round of communication that party speaks in. So on the one hand, we have upper bounds. These are protocols. Is there a question? So on the one hand, we have upper bounds. These are protocols that are highly resilient. Benno and Linial proposed in '85 the majority protocol, the n-bit majority protocol, where every party sends a random bit and then the output is the majority value. And the majority protocol is resilient to approximately square-root and adaptive corruptions. This is due to the central limit theorem, for example. In addition, they actually conjectured that this simple protocol, the majority protocol, is the optimal protocol with respect to adaptive adversaries. So there exists no protocol that is more resilient than the majority protocol. Now, on the other hand, we have lower bounds trying to match this upper bound. The first by Lichtenstein, Linial, and GTACS from '89 states that no single-bit, single-turn protocol, where single-turn means that every party sends a single message, speaks only once, and single-bit means that every message is just exactly one bit. So they showed that such protocols can never be more than screw-10 resilient. Next, Goldwasser-Kalla Park showed in 15 that no symmetric single-turn protocol can be more than screw-10 resilient. So a symmetric protocol is a protocol which output function is symmetric, that the identities of the parties don't matter, only what messages were sent. And last, Kallai-Komgotz-Raz extended those previous two results, showing that actually no single-turn protocol, no matter the structure, cannot be resilient to more than screw-10 adaptive corruptions. This means that for any single-turn protocol, there exists an adversary performing at most screw-10 adaptive corruptions that completely biases the outcome. So now we can move to our result. Like I mentioned earlier, Benno and Linial conjectured that majority is the optimal protocol. So this means that for every coin flipping protocol, we can completely bias it with screw-10 adaptive corruptions. And until now, the question of many-turn protocols was left unanswered. We only know results about single-turn protocols. And we closed exactly this conjecture. More precisely, we show that for any protocol, there exists an output value B, either 0 or 1, and an adaptive adversary performing at most screw-10 corruptions that sets the output of the protocol to B with overwhelming probability. Okay? So indeed, this proves the conjecture up to the polylog factor in the adversary. In addition, it's interesting to note that the one-sidedness of this result, namely the fact that we can only bias the protocol to some output value and not to an output value of our choice, is inherent. There exist protocols that cannot be biased towards 0 even with a linear amount of corruptions. And last, it's also interesting to note that this attack is even efficient in some settings, which is an improvement over the inherently inefficient attack of Kallai-Komgotz-Raz, since this attack was recursive. Okay, so now we know the history of coin flipping protocols, and I want to return to the statement I said in the beginning of the talk that actually lower bounds on coin flipping protocols induce limitations on the stability of random processes. And why is this true? Well, let's think about it. Every discrete random process can be thought of as a coin flip, right? We just take every step or change in this process, encode it as a message, and here we have a perfect description of this random process as a coin flipping protocol, right? We only need that the output of this random process is binary. Okay, so how can we use this fact to extend our result beyond only coin flipping? Let's see a concrete example. So let's say we have some classifier attempting to understand if a specific colony is consisted of giraffes or bunnies. And how does it work? We feed this classifier many samples of random animals from this colony, and then ask it to distinguish whether this colony was made out of giraffes or bunnies. And let's say all animals in the world can be either giraffes or bunnies for some reason. So we wish to understand how to fool this classifier. We want to change only a small amount of samples taken from the colony to fool this classifier to think that all of the colony is consisted of giraffes, or that this is a giraffe colony. So first of all, let's encode this as a coin flipping protocol. So every DNA sample, we encode to binary strings. And the output we encode is either 0 or 1, corresponding to if this colony is made out of giraffes or bunnies. And now, this is a coin flipping protocol, right? This, we know how to attack. So we attack this coin flipping protocol, and we know we can do this by corrupting only screw-10 of the parties. This corresponds to changing only screw-10 of the samples. This is really a small amount of samples. It's not too much. Now that we understand, now that we have this attack on the coin flipping protocol, we can put it back to understand where we need to intervene in this random process of the classifier attempting to understand the column. Okay? So this is just a private example of a general random process that we can show is not very resilient to fluctuations, adversarial fluctuations to be precise. Yes?
So this example uses a protocol which is very simple in the sense that it sends a signal around the messages. So do you have an example where the more general is that
Yes. So, yes. So Benny asked if we can, if there's an example for a more sophisticated attack that doesn't only rely on coin flipping protocols, which are single turn, right? Since this protocol, every party corresponds to a sample, and that party speaks only once. And we already know that we can buy single turn protocols. So a great question. Let's assume that this classifier receives samples from many different gene sequencers, for example. And changing a single sample is the same cost-wise as changing all samples produced by that machine. So this classifier is going to use 100 different gene sequencing machines. And if we alter a single sample of one of the machines, we can already alter all of the samples of that machine. So here, we can show that no matter how many samples are taken, we can tamper with only 10 of these machines. Does this answer the question? Excellent. So now I'm going to talk what are we going to talk about in the rest of this talk. First of all, I'm going to introduce the expected outcome martingale. This is the most fundamental tool in the analysis of coin flipping protocols. Then we will talk about single turn protocols. We'll try to understand how to attack them, and we will define what robust protocols are. These will be protocols that behave very nicely. Then we will describe a gentle attack on these robust protocols. What do I mean by gentle? This means that many of the properties of the original protocol are going to be preserved even under the attack, meaning that properties we had at the beginning are going to remain even as we go through our attack. And then finally, we're going to extend this to non-robust protocols as well, using exactly the gentleness of our attack on robust protocols. This will make much more sense later. Then in the end, we will talk about many-turn protocols, introduce the unique challenges in this setting, and describe our general attack approach. So let's dive right into it. We have the expected outcome martingale. So to talk about it, let's fix some L-round protocol pi, which is balanced, meaning that we get both 0 and 1 with probability half as the output. And we also slightly abuse notation in letting pi also denote the output function, which gets the transcript. So we also denote by message a random execution of our protocol pi, which is simply a vector of the messages of every round. Now we define the expected outcome at time k to be the expected outcome of the protocol conditioned on the first k messages. Let's try and understand what this means. So let's take our history, the first k-1 messages. We're going to now sample a random continuation of the protocol and check its output. So we just take expectation over randomly continuing this protocol. So now we understand what the expected outcome martingale is. This is MK. We also want to take a look at the protocol jumps. So these are the differences of the martingale. So what is the kth jump of the protocol? What does it represent? This represents the change in expected outcome induced by the kth message sent. So this corresponds to how did the kth message change our approximation of the protocol's outcome? Okay. So these are really important tools. If something is unclear, please do ask. So let's move on. Let's try and understand single-turn protocols. So we fix some single-turn protocol pi with n parties. Cleve showed in '86 that every single-turn coin flipping protocol has a jump of magnitude 1 over n. Okay? This quite readily implies a 1 over n one-shot attack. What does this mean? This means that there exists an adversary performing exactly one adaptive corruption that either increases or decreases the protocol's expectation by 1 over n. But this is not good enough, right? Since we want to completely bias the protocol, and this would require performing n of these one-shot attacks, which is way, way, way too much. But happily for us, Cleve and Pagliazzo showed in '93 that the situation is much better. They show that with constant probability, there exists a large jump. So this is a jump of magnitude at least 1 over square root 10 with constant probability, right? And this, again, implies a one-shot attack of magnitude 1 over square root 10, which means that with one adaptive corruption, we can either increase or decrease the expectation of the protocol by 1 over square root 10. And this seems to imply an attack by composition, right? We will take our initial protocol pi0, we attack it, increasing the expectation by 1 over square root n. Then we take this resulting protocol, attack it, and we do this iteratively again and again and again, every time increasing the expectation by 1 over square root n. Thus, completely biasing the protocol by only square root n such iterations. But unfortunately, this doesn't work, right? Since we're guaranteed that there exists a jump of magnitude 1 over square root n, but we are not guaranteed the direction of that jump. So it might be the case that pi0 has large jumps upwards. This is positive jumps. But once we apply this attacker, the resulting protocol pi1 has large jumps only downwards, so negative jumps. So we're stuck in some sort of zigzag where we first think we can bias the protocol towards 1, then we understand we can only bias it towards 0, and we can't really influence the protocol by much. So we want to devise a much more gentle attack. And why is that good? Well, like I said earlier, it's going to preserve properties of the original protocol. In particular, we want to preserve the property of the protocol being biasable towards 1. And then we won't have this situation of this zigzag where every time we can only bias it to a specific direction. So here's our attack. First of all, we want to attack gently, like I just said. So I want to talk about the advantages of attacking gently. The first is what I talked about earlier, properties being preserved even under attack. The second advantage is that the corrupted parties won't be leaked to the protocol. Since we discuss many turn protocols, we want to corrupt a party and leverage it to influencing the protocol over many, many rounds. So we can't afford the possibility of the protocol understanding that party is corrupted and expelling it from the protocol. Since now we sent one message from that party and then it's done, it's expelled, and we can't use it no more. So we treated it like corrupting it. We treat this by corrupting the messages, and this is not good enough, right? This would be like corrupting a protocol with n to the squared messages with one message in the single turn case, with the n messages in the single turn case. So we need to hide our corrupted parties. And then last but not least, a gentle attack gives us a much simpler analysis. Why is that? Since this attack is gentle enough, it preserves properties of the original protocol, which means that even under the attack, at every time, we're pretty similar to the original protocol. So when we perform the analysis, we don't have to ask ourselves, in what protocol are we now? How does it look? Because we know this looks very similar to the original protocol. So we don't have to all the time ask ourselves, what does the protocol look like right now? How did our attacks impact the protocol's execution? Okay. So now I'm going to introduce the most basic tool in our gentle attack. This is a tool that allows us to exploit a variance of a random variable to bias that random variable to have positive expectation. So how are we going to do that? Let's say we have some random variable y, which has expectation 0. This later on will correspond to a jump of the protocol. So we define the alpha biased variant of y. Alpha is just a parameter that specifies by how much we want to bias the protocol. So the larger alpha is, the more biased this random variable is going to be. How do we define the alpha biased variant of y? Well, the support remains the same. We only change the probabilities. So we have some value y of the random variable. We multiply its probability by 1 plus alpha times the value y. Okay? What does this do? This increases the probability of positive elements and decreases the probability of negative elements. So overall, we're increasing the expectation of our random variable. So this will correspond to biasing the protocol towards 1. Okay? To get a better understanding of this tool, let's see 2 examples. Okay? Let's say we have a random variable x that takes with a probability half either 1 over square root n or minus 1 over square root n. And let's see how the one biased variant of x looks like. So here we have the exact calculation, and it means that we favor with probability 1 over square root n the positive element. Okay? So we only slightly change the random variable, only giving an advantage of 1 over square root n to the positive element. On the other hand, let's look what happens when we change alpha to be square root n. In this case, we're going to completely favor the positive value. And this makes sense since I said earlier that alpha corresponds to by how much we want to bias the random variable. Okay. So now we want to get a real understanding of this tool. So we're going to have two claims talking about the properties of the biased variant. So the first ties between the expectation of our biased random variable and the variance of the original random variable. Okay, so more precisely, the expectation of the alpha biased variant of y is equal to alpha times the variance of y. And now I want just to mention that we have the technical detail in this transformation that y must be at least -1 over alpha. Why does this make sense? This relates to the fact that a random variable can be biased only by that much, right? If we could set alpha to infinity, this means that by remaining with the same support, we can change the expectation of our random variable to whatever value we want, but we know this is bound. So this is just an explanation to why this technical detail makes sense. And the second claim talks about the gentleness of this transformation. It states that the Kale divergence between the biased variant of the random variable and the original variant of the random variable is at most 2 times alpha squared times the variance, okay? And this is very similar to the expectation. So in some sense, this means that we change our random variable only by the amount that we gain in expectation in return to that change, okay? So we don't change it by too much. And these two claims give us a tight connection between the biased variant and the original variant, which will be very useful later on. Okay, so now we have this new cool tool, and we want to use it. So we define robust protocols. Our motivation is being able to apply our bias transformation with parameter alpha that is up to square root n, okay? So we just require that all jumps of the protocol are at least -1 over square root n. Later, we will use the gentleness of our attack in order to overcome non-robust protocols as well. Okay, so now we have robust protocols. I want to claim that the variance of a jump, these are the YKs, the change in expectation induced by the messages, is a good measure of how important that jump is going to be. Why is that true? Let's say we have a jump with small variance. I claim that the influence it has over the outcome is small. Why is that true? We can apply Cheryshev's inequality, for example. So a jump that has small variance is going to be very concentrated around 0, thus not having much influence over the final outcome of the protocol. And this means we can just ignore this jump since it doesn't matter too much. On the other hand, if a jump has large variance, then this means it potentially has large influence over the outcome. Why is that? Since we can simply apply the bias transformation to increase the expectation of that jump, causing an increase in the expected outcome of the protocol. And this means that we can leverage this party to biasing the protocol. So just to reiterate, we introduced this new tool of the alpha biased variant of Y. And then we're going to attack robust protocols, which are just protocols that we can apply this tool with parameter alpha, which is up to square root n. Okay. So now let's describe the adversary. Just a quick reminder, YK, this formally was the change in expected outcome induced by the kth message. Really, I repeated that much because this is one of the most important parts of this analysis. And we're going to classify these jumps as either big jumps, large jumps, or small jumps. So a jump is going to be called large if and only if its variance is at least 1 over n, okay? In the slides, we're going to have this technical detail, a function which is little omega of 1. We're usually going to ignore it, but you can just think of this as log n, for example. So how is our adversary going to work? At every round, it's going to do the following thing. We denote by PK the conditional distribution of the next jump. Now we ask ourselves, is this jump a small jump or a big jump? If this is a small jump, we know from earlier we can just ignore it without caring much, since it doesn't influence the final outcome by too much. On the other hand, if this is a large jump, we would like to crop it, we would like to crop the party holding that jump with some probability. More precisely, we're going to want to crop that party with probability proportional to the standard deviation of that jump. And if we decide we actually want to corrupt this party, we're going to send its message according to the bias distribution of PK with parameter alpha that is 1 over the standard deviation. Okay? This now might seem very weird. Why does it make sense? What are these magic numbers? So as a sanity check, let's see how this acts on the majority protocol. So in the majority protocol, all jumps are of magnitude approximately 1 over square root n, meaning that their variance is 1 over n. So all jumps are indeed large jumps. And this means that we would like to corrupt them with some probability. And that probability is the standard deviation of the jump, which is 1 over square root n, right? So what's going to happen? We're going to corrupt a random subset of square root n parties. And now what will happen once we corrupt those parties? Well, this is exactly what we've seen in the second example earlier when we talked about the bias transformation. So this is a jump that takes either plus 1 over square root n or minus 1 over square root n with probability half. Yes, with probability half, since this is a random bit. And we're going to bias it with parameter 1 over square root the variance, which is square root n. So we're going to take that message and just set it to the constant 1. So how is this going to look like? We're going to sample a random string of length n, and then we're going to set square root n indices to 1. But this is already constantly probable as an honest execution where the output is 1, right? From the central limit theorem, we expect that if the outcome is 1, we'll have a surplus of approximately square root n 1s. So this means that we didn't change the biased execution by too much. Does this make sense? Okay. So now that we've seen that this indeed works on the majority protocol, yes. Oh, great question. So this is a technical detail I was hiding. So let's say we have some mapping between, oh, sorry. So the question was, how do we understand what message we need to send so that the jump will distribute like the biased distribution of PK? So we have some mapping between, between messages to the jumps they induce. So we apply this mapping to come from messages to jumps. So now that we have the bias distribution we want to sample the jumps from, we can just pull back using the inverse of this mapping. So we just, so we know what jump value we want to produce, and then we're going just to select one arbitrary message that produces this jump value. Any more questions regarding the adversary or robust protocols? Okay, excellent. So now we want to show that this works for every protocol, right? We don't want this to work only for the majority. So this will consist of two steps. First of all, we're going to show the quality of the attack. So we're going to show that the output of the attacked execution is 1 with overwhelming probability. We're going to bias every protocol to 1. And the second step is showing that our adversary doesn't perform too many corruptions, right? These are exactly the two ingredients of a successful attack. But before we begin with the analysis, I want to make some observations about this attack. So we denote by x1 to xn the attacked execution, the jumps of the attacked execution. So what are these x's? These are the jumps that correspond to the change in expected outcome given our attacked history. So previously, when we talked about protocol jumps, they had expectation 0. These jumps are not going to have 0 expectation since these correspond to jumps after we might have biased them, right? When we bias messages, we want to increase the expectation of the jump. So I want to explain a bit more what exactly this means. So this is the different sequence of the process that is at every step, assuming that the rest of the protocol is going to be sampled honestly and taking expectation over that. So we can define our process, say, ON, which at every step is the expected outcome if we would have continued this protocol honestly, but conditioned on the attacked history. And x1 to xn is exactly going to be its different sequence. Okay, and now we're going to have a really weird random variable. This is y1 to yn. It's going to be jointly distributed with x1 to xn in the following way. At every step of the protocol, before we decide what message we're going to send, or before that message is sent according to the honest parties, we're going to sample an independent copy of PK. So what does this mean? Before we send our biased message or the honest message, but this might be the biased message, we're going to sample a random copy of the jump if it were taken honestly. So what exactly is y1 to yn? This is the protocol jumps, but using attacked history. So this is the jumps of the protocol if they were sampled honestly, but using the attacked history. This really is a very weird object, since it doesn't make sense if we don't do anything else with it. It isn't an object we would have defined to understand the coin flipping protocol, but it stands in the base of our analysis and attack. Okay, so now I want to show, rather informally, that the expectation of xk corresponds to the variance of yk. But this is only true for large jumps, since for small jumps, we don't corrupt their messages, and thus their jump is actually sampled honestly. So the expectation of small jumps is always 0, right? Okay, so why is this true? Let's assume that we've decided to corrupt the party holding the kth message. So the expectation of xk conditioned on the history and the fact that this party is corrupted is equal from our claim on the biased distribution, 1 over the standard deviation times the variance of that jump, right? Of that jump if it was taken honestly, of pk. And if we multiply these, this is just square root the variance. But we don't always corrupt a party, right? We corrupt it with some probability. And what is that probability? For a large jump party, we corrupt it with probability proportional to the standard deviation. So square root the variance of yk times some omega of 1. And if we multiply these, we can compute the expectation of xk. So what is the expectation of xk? It's the probability we decide to corrupt the kth party times the expectation we would gain if we would have corrupted that party, right? Since if we do not corrupt that party, the expectation of the jump is going to be 0, since it's going to be sampled honestly, and sampling it honestly means that we just take a random continuation, not affecting the expected outcome, since we're not doing anything active. Okay, so now we know how to tie between the expectation of xk and the variance of yk. This is exactly like the claim on the biased distribution, only applied on our protocol and the fitting random variables. So from this, we can draw the main observation in our analysis, which is that the variance over the yks is little o of 1. This is true since roughly, I'm ignoring some details, that the expectation of xk is equal to the variance of yk, and the expectation of xk is between 0 and 1, since this corresponds to the output, right? Half plus sum over all jumps is going to be the output of the protocol. And this is always between 0 and 1, which means that omega of 1 times the variance is somewhere between 0 and 1, meaning that in total, the variance is little o of 1. So just to reiterate, we showed that the variance of the sum over the jumps, if they were sampled honestly, but conditioned on the attacked history, is little o of 1. And really, I just want to say again that this object of yk is very weird, but it plays a very important role in this analysis. Okay, so now we want to show the quality of the attack. So first, another claim regarding the bias transformation. I want to claim that given some 0 expectation random variable y, we can couple it with its biased variant in such a way that the alpha biased variant of that random variable is never less than the original random variable. Why is this true? This is true since we only increase the probability of positive elements and decrease the probability of negative elements. So we can think of it as converting some of the negative elements to positive elements. And overall, we never change an element to be less than its original value. And using this claim, we can couple xk and yk in such a way that xk is always at least yk. This is since, again, xk are the biased versions of yk, right? Since yk corresponds to pk, and xk is the jump actually taken, so it might be biased. Okay, so why does this imply the quality of the attack? Well, we're going to show that the probability that the output is 1 is overwhelming. So using the coupling, we can show that the probability that the output is 1 is at least 1 minus the probability that the absolute value over the sum of yk's is at least half. And using Chebyshev, we can bound this by 1 minus 4 times the variance, which by our core observation is at least 1 minus the log 1. This is exactly applying the core observation. Okay, so we're a bit short on time, so we'll take this more quickly. So now we want to show the corruption budget. We want to show that we do not perform too many corruptions. Instead, we're going to show that in expectation, we don't perform too many corruptions. Why is this enough? Well, from Markov inequality, we know that we're going to perform more than square root n times log n corruptions only with probability at most 1 over log n. And in such a case, we can just instruct the adversary to abort, and only with very small probability this would even happen. So overall, it doesn't impact our adversary. It doesn't impact the attack, preserving the quality. So this proof is really just substituting all the values. So we're going to skip it. Nothing interesting happened. Okay, so now we want to extend our attack to non-robust protocols as well. How are we going to do that? Well, we're going to attempt to transform an arbitrary protocol into a robust protocol and then apply our attack. But we're going to have the guarantee that if we fail, then this protocol is already going to be completely biased towards you. And just to reiterate, the protocol being robust means that every jump is at least minus 1 over square root n. So we're going to make use of the following claim that we used informally when discussing the case of Kleber in Pagazzo. So the claim is that if with probability, at least alpha, there exists a large jump downwards, this is a jump that can take a value of less than minus 1 over square root n, then there exists a one-shot attack that decreases the expectation by alpha over square root n. This is simply waiting for that jump and then sending a message that leads to the smallest value possible. So how are we going to transform our protocol into a robust protocol? Well, we're just going to eat all of the bad jumps. These are jumps that are large negative jumps. So we take our protocol pi 0 and we apply this one-shot attack as long as there exists a large negative jump with, say, constant probability. Now let's look at the final protocol, pi n. We know that its expectation is at least 0, and the expectation of the original protocol is at most 1. And every time we apply the attacker, we decrease the expectation by at least 1 over square root n. So in total, we apply this at most square root n times. So now we review our final protocol. If its expectation is little log 1, we're done, right? Since we performed only square root n adaptive corruptions, and the outcome is little log 1. But if the expected outcome of the protocol is constant, then we know the protocol is close to being robust, since we stopped performing this one-shot attacker. So only with very small probability, there even exists a large negative jump. And in this case, we can just apply our gentle attack, since it preserves the property of being close to robust. And if the protocol is being close to robust, then we don't encounter a non-robust jump, which interferes with our adversary. So the attack will just go through as usual. Okay, so this is a very interesting thing that is, in some sense, one of the most important observations of our attack. So just to reiterate, we defined robust protocols, then we understood how to attack robust protocols, and then we extended this using the gentleness to non-robust protocols as well. Okay. So now let's move on to many-turn protocols. I'm going to skip the examples. So let's talk about the main obstacles in the setting. So the first is that the greedy attack always fails or might fail. Why is that? Well, if we act too greedily, the protocol might understand what the corrupted parties are and expel them from the protocol, and in that way, we won't be able to use them. For example, we can look at a many-turn majority where if a player sends too many consecutive ones, it's expelled from the protocol. So if we act too greedily, we're not going to have any impact over the protocol. And this wasn't a problem in the single-turn case, since parties were disposable. They spoke once, and then we didn't care about them. Another obstacle is even understanding which parties to corrupt, since the influentiality of a party isn't known in advance. That party is going to send many, many messages, and how it's going to affect the protocol depends on the messages of other parties as well. So we can't predict this. And this wasn't a problem in the singleton case, since we knew exactly its influence before we had to decide whether or not to corrupt that party, since we could go over all possibilities of the next message and understand how it affects the protocol. Okay, so now the attack approach. Large jumps are going to be treated exactly like the singleton case. Okay, so we're going to corrupt them with probability proportional to their standard deviation and then send the corresponding message. On the other hand, small jumps are now going to be corrupted on a per party basis. So even once we corrupt a party, we're only going to slightly bias its message since we need to use it over many rounds. And how are we going to understand when to corrupt that party? Well, the nice thing is that we're going to do this totally at random with probability 1 over square root 10. But there might be a problem, right? Let's look at an n to the 4th majority protocol where only one party speaks. All of its jumps are small, but we have to corrupt it in order to influence the protocol. So we partition every party into small pseudo parties where every such pseudo party has only, say, variance 1 over n. That way, giving many chances to become corrupted, since now we're going to corrupt the pseudo parties. Okay, so this is exactly how we treat the many turn case. If you have any questions, ask after the talk. I'm just going to summarize it since I'm already flowing. So we showed that the symmetric single-turn uniform bit protocol, the majority protocol, really the simplest protocol possible, is the optimal protocol with respect to coin flipping, with respect to adaptive adversaries. And this closes the conjecture of Benno and Linial from 85. In addition, we have a work in progress that uses strongly adaptive adversaries instead of adaptive adversaries. These are adversaries that can decide whether or not to corrupt the party after they've seen the message that party sent. And in this case, our attack can be made two-directional, meaning that we can decide to what output value we want to bias the protocol. In addition, this attack is efficient in much more settings. Practically, if the protocol is full coin, our attack is efficient. And now there are some interesting open questions left. So the first is achieving all but negligible bias. Here we understood how to set the outcome to B with probability 1 minus little o 1, but we might want to set the output to 1 with all but negligible probability. So it's interesting to understand whether or not this is possible. And after that, it's very interesting to understand the optimal ratio of corruptions to bias, namely understanding exactly how many corruptions are needed to achieve a specific bias and trying to match that to the bound given by the majority protocol. So this is it. Thank you all for listening, and I hope you enjoyed. Yes.
Any chance to get rid of the polyload penalty?
So we can't completely bias even the majority protocol using only square root n corruptions, right? This is only going to change the outcome by a constant. Yes, so Benny asked whether it's possible to get rid of the polylog factor in our adversary. So we can't bias the protocol using only square root n corruptions, but it's an interesting question to understand exactly what this factor needs to be. In the majority protocol, that factor is going to be, I think, square root of log 1 over the bias you're trying to achieve.
Just say you want to bias it to 0.29, right? Probably the 0.9, you want the output to be 1. Okay, probably the 1. So can you do it with square root n output in general? Like for majority, all the square root n is sufficient, right?
Right. So I think that if we, so the current approach doesn't allow that. The current approach is very simplistic in the sense that you saw all the tools we used. They're really not that complex. We only talked about expectation and variance, and thus we can't achieve an optimal result. And we heavily rely on the fact that we completely bias the protocol. In order to achieve a constant bias, this is possible, and I think it's possible even with square root n corruptions exactly, for sure in the strongly adaptive case. we can use a different approach where at every time we're going to perform one corruption, trying to gain at least 1 over square root 10. But you need to you need to dive deeper to understand exactly the constants, and because here we have this omega of 1, which we ignored, but plays an important role in the ratio between the variance and the outcome of the protocol. Thank you. Yes.
Connections to two